Graphing. When we graph, and you will graph a lot in this class, there are some things that are required on all of your graphs. Your graphs need a title. That might be distance versus time. It might be average velocity versus time. But it'll tell you what's on the x-axis and what's on the y-axis. So you need to title your graph. Your axes need to be labeled with both the quantity, what you're measuring, and what the unit is. For example, if one of my axes was a mass, I would say it's mass, and then I would put parentheses, kilograms, that's the unit that I'm using for mass. Or if for some weird reason I was using grams, I would say grams, but we usually use kilograms. The graph should be big, 2/3 to 3/4 of a page. If I have a graph, this is my paper, and I make my graph big, but all of my data is right here, that is not a big graph. Make your scale, the scale is the number range that you put on each of the axes, only slightly bigger than the range of data. So if all of my data has fit in this tiny little part of my graph, then I should have taken the scale and stretched it to take up more of my axis. And in this case, I should have done that on both of them. I should have taken this scale and made it take up the entire x-axis instead of some little part of it. Okay? Never, ever, ever connect the dots on a graph. Now you do in math, because when you graph in math, you're graphing a function, and all of the answers that you get when you plug things into your function are by definition on your line or your parabola or your hyperbola or whatever. But in physics, that's not the case. In physics, you have data points, and your data points are not going to make an exact line or an exact parabola, and so you don't connect those dots. You draw a line, which might also be a curve, of best fit for all of your graphs. Never just connect the dots that are there. Always draw a line of best fit. It's kind of like the average of the line. So here's a good graph. It's a distance versus time squared. Okay, when I use that terminology, when I say, distance versus time squared, it's whatever's on your y-axis versus what's on your x-axis. So a distance versus time squared graph, distance is on the y-axis and time squared is on the x-axis. Notice the quantities here in the unit, the quantities here in the unit, the scale. In this case, the last data point hits the top and the limit on the y and the x-axis, so it's taken all of the space that's possible. These little blue things are the data points, but they aren't connected. You don't just go from here to up to this one to that one. And okay, I know I'm not drawing straight lines, but you get my point. It's not a dot-to-dot exercise. These data points show a trend, so you don't just connect them like that. You draw the average, so you take a ruler and you lay it down, not so that it connects them all, not so that it touches them all, but so that it kind of goes in between. If you look, there's a couple points on top. So this one's a little higher, and this one, and this one, and this one are a little higher. This one's a little lower. This one's a little lower. That red line is the line of best fit, or it's also called the trend line. It is the line that represents kind of an average of those points. Let's graph some data. This is just some data I made up. We're going to draw a distance versus time graph. So we're going to put distance on the y-axis and time on the x-axis. So we need to draw our axes. Now, it's hard for me to draw a perfectly straight line in this program. So I would expect you to have a ruler. And while there is a ruler, maybe it'll help me. I'll put it down. And I can twist it around. Make it vertical. Okay, I'm going to move it. Sorry, this takes a minute. Okay, and then will this let me draw? Yes. I thought. Sorry. I'll edit this out. Okay, we're going to graph some data. We have distance and time. We're going to do a distance versus time graph. So distance will be on our y-axis and time will be on our x-axis. So I'm going to take my ruler and I'm going to draw my vertical axis. Hopefully this will make a nice straight line for me. I just ran out of space. Program's acting a little funny here. 1 second. See if that's good enough. Yeah, that's good. And then let me flip this around. Make it horizontal. And I'll draw my x-axis. So I can make it horizontal. There we go. Oops. Okay, this is supposed to make it go right along the ruler. And so it's not squiggly. Pretend it's not squiggly. Okay, I'm going to move it just a little bit because I want my x-axis to go a little further. Now I'm done with my ruler. Okay. Always do graphs in pencil. It's actually a big rule. Graphs are in pencil. Okay, so let's look at my scale. I need my time, and this axis is time to the nearest, and the unit is the second. And this axis is distance. And it's in meters. So I need to spread 3.6 meters along the y-axis. Let's say 4 meters. So our scale is not quite as big as our distance. So let's count these squares and see how I'm going to split up 4 meters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Ooh. If I go all the way up to the top, it's 20. And that's nice because if the top is 4 and there are 20 spaces, then every 5 spaces is 1. So 1, 2, 3, 4. This is 1 meter here. And then 1, 2, 3, 4. That's 2 meters. 1, 2, 3, 4. This is 3 meters here. And then 1, 2, 3, 4. And then 4 meters. Okay? So that was easy. Now my time scale, it needs to go up to 8 seconds. So let's count our squares and see how we're going to divide it up. So 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. This is 24, 25, 26, 27, 28, 29, 30. I could go out to 32, but I think I'm going to use 24. And I'm going to let every 3 blocks be 1. So every block will be a third. So here's 0. And 1, 2, 1. 1, 2, 2. 1, 2, 3, 4, 5, 6, 7. Sorry, 7. And then 8 seconds. Okay, so I'm pretty much taking up my whole graph. So now let's plot some points. 0, 0, that's it. Now the origin might or might not be a point on your graph. Sometimes it is, sometimes it's not. At 1 second, it's gone half a meter. So at 1 second, half would be right there. If 5 spaces is a whole, then a half. So here's a point. And at 2 seconds, it's 0.9. 2 seconds, so not quite 1. This would be 0.8. So 0.9 would be in between. That would be 0.2, 0.4, 0.6, 0.8, and then a half would be 0.9. At 3 seconds, 1.6. 3 seconds, there's 1, 1.2, 1.4, 1.6. 4 is 2.1. So 2.2, 2.1 is halfway in between. At 5 seconds, 2.4. There's 2.2, 2.4. At 6 seconds, 2.8. At 7 seconds, 3.1. 7, 3.1. And at 8 seconds, 3.6. So here's 8, 3, 2, 3.6. Okay, so notice that the data has a trend that's a straight line, but it's not exactly. And so I need to draw my trend line. So I'm going to bring that ruler up again and see if I can draw a trend line. Now my ruler is shorter than my line here. Okay, now that's not steep enough. You can see it's below all of these up here. So I'm going to make the ruler go a little steeper. Move it. Make it a little steeper. Move it. Your ruler will be longer than any data that you take. And now I'm going to draw the trend line, and hopefully my trend line will stay along this ruler. Now ordinarily I would start way down at the bottom, not necessarily going through that point. The 0, 0 point is not any better data point than any of these others. So I'm going to put my pen down. Okay, I'm going to slide my ruler up to continue my trend line. And draw it on in. Okay. Oops, it didn't draw it yet. No, I think it did. Okay, now move. Yes, it did. So I'm going to close my ruler, and that's my trend line. So my data doesn't touch it all, but there's some points that are below and some points that are higher. And so that's how I draw a graph. So I found the scale for both axes. I labeled both axes. I don't have a title. This is a distance versus time graph. So now it has a title. It's big. I labeled axes with the quantity and the unit. I did not do a dot to dot. I did a trend line. Now the next thing that you may have to do is find the slope. And remember, the slope is y2 minus y1 over, you've done this in math before, so don't be freaking out. This is easy. x2 minus x1. You never, ever use data to find the slope. You always use your trend line. And so find 2 points on your trend line. This looks like a nice point, easy to read. So I'm going to use that point. That point is 2, 1, right? 2 on the x-axis and 1 on the y-axis. Now I found another point that's easy to read. So I like this one. This point is 5. And I go straight over 2.2. So my slope, remember m is slope, y2, so that's 2.2, minus y1, which is 1, divided by x2, 5, minus 2. 2.2 minus 1 is 1.2. 5 minus 2 is 3. And if you give me just a second, I'll pull up my calculator. Okay, and on my calculator, I could do that in my head. That's 0.4, because 12 divided by 3 is 4. So I'll do it on my calculator just to make sure. 1.2 divided by 3 equals, yes, it's equal to 0.4. Now slopes have units. Y-axis was meters, x-axis was seconds, so that's 0.4 meters per second. And that's a speed, or a velocity. So if this object was at these places at these times, then it had an average velocity of 0.4 meters per second. So now we have graphed data, and we have found the slope and determined the physical significance of that slope for the graph. So title, axes labeled, don't connect the dots, draw your trend line. Your slope must not be found with data points, but found with points on the trend line. And now we're done. Thank you.